Imagine yourself adrift in the vast emptiness of space. Billions of stars glitter in the distance, but here, there is only darkness and silence. Then, you feel it. A subtle tremor, a shiver that seems to pass right through you. This is a ripple in the very fabric of the universe, a gravitational wave. It's a phenomenon so strange, so profound, that it took one of the greatest minds in history to predict its existence. That secret would be unlocked by a man named Albert Einstein. And it all began with a revolutionary idea that gravity is not a force but a curve in the very fabric of space and time. Before Einstein, we saw gravity as a force acting across vast distances. But Einstein saw something different. He imagined gravity not as a force but as a consequence of the shape of space-time itself. Massive objects like stars and planets warp the fabric of space-time around them. It's not that the Earth is being pulled towards the Sun, it's simply traveling along the curved path created by the Sun's mass. Einstein realized that if massive objects could curve space-time, then objects moving rapidly, like two stars orbiting each other, would create ripples in this fabric. These ripples, he predicted, would travel at the speed of light, carrying energy away from the source. We now call these ripples gravitational waves. They are the echoes of some of the most cataclysmic events in the universe: colliding black holes, exploding stars, even the birth of the universe itself. But even Einstein had his doubts whether we'd ever actually detect these elusive waves. For decades, scientists were faced with an almost insurmountable challenge. Gravitational waves are incredibly weak, barely noticeable tremors in space-time. In the early 20th century, we simply didn't have the technology to even attempt to detect these waves. Even Einstein himself was doubtful. He knew the math, he understood the implications of his theory, but even he questioned whether we'd ever have the means to confirm his predictions. The technology needed to detect gravitational waves seemed like something out of science fiction. The first glimmer of hope came in the 1970s with a discovery that would change everything. Two astronomers, Russell Hulse and Joseph Taylor, were studying pulsars, rapidly rotating neutron stars that emit beams of radiation. They stumbled upon something extraordinary, a binary pulsar system, two pulsars locked in a gravitational dance, orbiting each other at incredible speeds. If Einstein was right, this system should be losing energy, radiating it away in the form of gravitational waves. Hulse and Taylor meticulously tracked the orbits of these pulsars over several years. The pulsars were indeed losing energy, and their orbits were decaying, spiraling inward at a rate that matched Einstein's predictions with incredible precision. This was a watershed moment. Hulse and Taylor's groundbreaking discovery earned them the Nobel Prize in Physics in 1993. The discovery of the binary pulsar system was a major breakthrough, but the dream of directly detecting gravitational waves remained elusive. This led to the development of LIGO, the Laser Interferometer Gravitational Wave Observatory. Instead of looking for light, LIGO would listen for the faintest whispers of gravitational waves. Imagine shining a laser beam and splitting it into two paths. If a gravitational wave passed through, it would stretch and squeeze space-time itself, ever so slightly changing the length of the laser beam's paths. LIGO was designed to detect even these minuscule variations. At the heart of LIGO were lasers, mirrors, and incredibly precise measurements. Each LIGO facility consisted of two arms, each 4 kilometers long, arranged in an L shape. When the two laser beams recombined, they interfered with each other, creating a telltale pattern in the recombined laser light. Building LIGO was a monumental undertaking, requiring the collaboration of hundreds of scientists and engineers from around the world. The first LIGO detectors began operating in the early 2000s, but for years, they heard nothing. And then, on September 14, 2015, everything changed. September 14, 2015 began like any other day at LIGO. But then, at 5:51 a.m. Eastern Time, a signal appeared in the detectors. This signal had a distinct shape, a characteristic chirp that scientists had predicted for years. It was the telltale signature of a gravitational wave, and it was coming from a source billions of light-years away. The near-simultaneous detection at both locations, thousands of miles apart, ruled out any local disturbances. This was the real deal. By analyzing the shape and frequency of the chirp, scientists were able to determine that it came from the merger of two black holes, each about 30 times the mass of our Sun. The final moments of this cosmic dance were a symphony of violence as the two black holes collided and merged into a single, even more massive black hole. The energy released in this cataclysmic event was unimaginable, and it was this energy, carried by gravitational waves, that LIGO had detected billions of years later. The detection of gravitational waves was more than just a scientific breakthrough. It was a resounding confirmation of Einstein's genius. A century after he first predicted their existence, we had finally observed these ripples in spacetime, and they behaved exactly as his theory predicted. It was a triumph not just for Einstein but for the scientific method itself. The detection of gravitational waves marked the beginning of a new era in astronomy. For centuries, we have explored the universe using light, visible light, radio waves, X-rays, and gamma rays, but gravitational waves offered a completely new way of seeing the cosmos. Unlike light, gravitational waves are not absorbed or scattered by matter. With gravitational wave astronomy, we can now study objects and events that are invisible to traditional telescopes. That first detection of gravitational waves in 2015 wasn't just a single event. It was the opening note of a cosmic symphony. Since then, LIGO and its European counterpart Virgo have been listening to the universe, picking up the faint tremors of distant cataclysms. With gravitational wave astronomy, we're not just seeing the universe, we're listening to it. Each chirp, each burst of energy tells a story. More than black holes. Expanding the gravitational wave repertoire. While the first gravitational waves detected came from merging black holes, these cosmic ripples aren't limited to just these enigmatic objects. The universe is a violent and energetic place, and many events can send gravitational waves rippling outward. Imagine two neutron stars, the incredibly dense remnants of collapsed stars, locked in a deadly embrace. As they spiral closer, they distort spacetime, sending out gravitational waves that carry away energy and angular momentum. Finally, they collide in a spectacular explosion, a kilonova, that can outshine an entire galaxy for a brief shining moment. These kilonovas are thought to be the cosmic forges where heavy elements like gold and platinum are created and scattered throughout the universe. And with gravitational wave astronomy, we can witness these events firsthand, studying the physics of matter at extreme densities and temperatures. But it's not just about the big explosions. The future of listening, a symphony yet to be heard. We're still in the early days of gravitational wave astronomy. It's like having just invented the telescope and pointed it at the sky for the first time. We've glimpsed a few stars, a few galaxies, but the vast majority of the universe remains unexplored. But the future is incredibly exciting. New, even more sensitive gravitational wave detectors are being planned and built around the world, creating a global network that will allow us to pinpoint the sources of these cosmic ripples with incredible accuracy. Imagine being able to trace a gravitational wave back to its source, to see the aftermath of a black hole merger, or the fading glow of a kilonova. With future detectors, this will become a reality. And then there's the possibility of detecting gravitational waves from the very early universe, from the epoch of inflation, the fraction of a second after the Big Bang, when the universe underwent a period of exponential expansion. These primordial gravitational waves would be a window into the universe's earliest moments, providing clues about the nature of gravity itself. A new window to the universe beyond electromagnetic radiation. For centuries, our understanding of the cosmos relied on electromagnetic radiation. Light, in all its forms, has been our cosmic courier. But light has its limitations. It can be absorbed by dust and gas. Gravitational waves are different. They are ripples in space-time, unimpeded by matter. With gravitational wave astronomy, we've opened a vast new portal. The invisible universe unveiling dark secrets. The universe, as we're coming to understand it, is a much stranger and more wondrous place than we ever imagined. It's filled with objects and phenomena that defy our everyday experience. Black holes, neutron stars, dark matter, and dark energy, to name a few. These enigmatic entities don't emit light, or at least not light that we can easily detect. They lurk in the shadows, their presence inferred from their gravitational influence on the visible matter around them. Gravitational waves offer a way to pierce this cosmic veil, to study the invisible universe in ways we never thought possible. We can now see black holes colliding, witness the death throes of massive stars, and perhaps even detect the faint whispers of the Big Bang itself. It's as if we've been handed a cosmic flashlight, a tool that allows us to illuminate the darkest corners of the universe, revealing the hidden workings of gravity and the secrets of the cosmos's most extreme environments. Albert Einstein, with his revolutionary theory of general relativity, didn't just change our understanding of gravity, he changed our understanding of reality itself. He showed us that space and time are not separate entities, but rather interwoven threads in the fabric of the cosmos. And just as a stone thrown into a pond creates ripples that spread outward, Einstein predicted that massive objects moving through space-time would generate gravitational waves, ripples in the very fabric of the universe. It's a testament to his genius that it took us a century to develop the technology sensitive enough to detect these incredibly faint whispers from the cosmos. But detect them we have, and in doing so, we've confirmed Einstein's vision with astonishing precision. His legacy lives on, not just in textbooks and lecture halls, but in the very fabric of the universe itself. Every gravitational wave we detect is a tribute to his brilliance, a ripple in the river of time carrying his ideas across billions of light years. Riding the waves of gravity. The detection of gravitational waves marks the beginning of a new era of exploration. Imagine a future with a network of detectors on Earth and in space listening to the cosmos. We'll pinpoint sources with incredible accuracy, creating a 3D map of the universe. Study black hole and neutron star collisions, and detect whispers of the Big Bang. We stand on the threshold of a new age, listening to the universe's faintest tremors. The future of our understanding of the cosmos is bright and filled with the music of gravity. Section 1. The Echoes of the Universe, a New Age of Discovery. As we stand on the precipice of this new era in astrophysics, it's essential to reflect on how far we've come. From Einstein's theoretical musings to LIGO's groundbreaking detection, our journey with gravitational waves is a testament to human curiosity. The discovery of these ripples in spacetime has expanded our ability to perceive the universe in a way that was previously unimaginable. Gravitational waves offer insights into phenomena like black hole mergers and neutron star collisions. These waves enable us to study the universe in its most violent and energetic states. The detection of gravitational waves has opened a new window into the universe. Unfolding the mysteries of the cosmos. Einstein's theory of relativity provides a robust framework for understanding gravity. The detection of gravitational waves highlights potential new physics beyond Einstein's predictions. Delving deeper into the universe may challenge our current understanding. The exploration of gravitational waves is just beginning. Advanced detectors will capture weaker and more distant signals. This will help us probe the universe's earliest moments. Studying gravitational waves could lead to breakthroughs in understanding dark matter and dark energy. Observing these interactions may reveal their nature and influence. The journey beyond Einstein holds the promise of profound discoveries. Each detection of gravitational waves reveals hidden complexities. Our quest to unfold the mysteries of the cosmos honors Einstein's legacy. Section 3. A Symphony of Knowledge. The future awaits. The story of gravitational waves is a symphony of knowledge, composed of the efforts of countless scientists, engineers, and visionaries. As we look to the future, the possibilities for discovery are boundless. The detection of gravitational waves has revolutionized astrophysics, but we are only scratching the surface. Future projects like LISA promise to expand our observational capabilities. These instruments will detect waves from supermassive black hole mergers and primordial waves. The symphony of gravitational waves will continue, deepening our understanding of the cosmos. Each discovery adds a note to the symphony, inspiring future generations. As we ride the waves of gravity, we are reminded of the power of human curiosity. The detection of gravitational waves has marked the dawn of a new era in astronomy. The future awaits, filled with the promise of discovery and the symphony of knowledge.